Hey guys, welcome back. This is going to be our last part for polygons before we move on to parallelograms and quadrilaterals. So the 2 days that we spend in class tomorrow, or sorry, not necessarily tomorrow, but next week, whether it's Monday or Tuesday or Thursday or Friday, they're going to be a little bit more challenging. We've really just kind of done one set of topics here with polygons to kind of stretch it out for the whole week. But I wanted to do the harder stuff in class, okay? So make sure that you have this assignment, which is really just a review, and I'll show you a few new things at the beginning. Make sure you have it done before we come back in person, whether you're meeting on Monday and Tuesday or Thursday and Friday. All right, so, and again, of course, if you have any questions, please make sure that you ask. I really enjoyed having you guys in class. Like, this has been a really exhausting week for me because, I mean, I'm up right now recording this at 11 o'clock at night, and I still got to make the stats video. I know, woe with me, but it's okay. I live off of the energy that I have from just being able to be with you guys in class. So really enjoy that. So thank you, and I'm looking forward to seeing you guys next week and for a full week, my A students, Monday and Tuesday, not just Tuesday. So I'll see you guys then. All right, let's get right into this. So let's do a quick review of some of the angles of a polygon. So if we have a three-sided polygon, we call that trigon, right? Just kidding. Triangle. And I forgot to lock those in place. Let's see if I can do that real quick. Boom, magic. All right, number of triangles in a triangle, well, there's one of them. And then the sum of the interior angles of a triangle is going to be 180 degrees, right? We've proven that several times at this point, but anyway, good to go. Next thing we have is a four-sided figure, which is a square. In this case, we just call it a quadrilateral, and this is true for all quadrilaterals, whether regular or irregular. I'm just showing you the regular ones because they're pretty. All right, moving on. Number of triangles we have. If we go from one diagonal to the other, are two interior triangles that we have, and so the sum of the interior angles is going to be 180 for this one and 180 for that one. So two triangles, a sum total of 360 degrees for all the interior angles for a quadrilateral. Same thing, seven-gon now. Oops, I'm jumping, but we should be okay. Seven-gon in this case is technically actually heptagon or septagon. There are two less triangles than there are the number of sides, so I don't even have to count. I know there's 5 of them, right? That was the pattern that we realized. Kind of helps us with our general form and our formula anyway. All right, so 5, the number of triangles, times 180, which is going to give me 900. All right. Then we have 11 sides on this one, which is an undecagon. You can also call it an 11gon if you're not sure. That's kind of a weird one. But just think about it, it's a decagon with un more, which is like 1 more than 10. So undecagon, just like dodecagon, I guess like dos, like uno and dos, and then tri is not like tres. I don't know. But it's all got Latin roots, and so that's where it all comes back to. Same thing. All right, so undecagon, 11. 11 minus 2 would give us 9. And then 9 times 180, which is going to be, I don't know, 1260, because I didn't want to get my calculator out. So lazy. All right, next one, we have an n-gon. So if we have a generic n-gon, which has n sides, it's called an n-gon. The n number of sides, the number of triangles is always 2 less than that. So regardless of how many sides you tell me we have, there's always going to be 2 less triangles. So that's where we get our form of n minus 2. And then we can take the number of triangles, multiply that by 180. So if you notice here, everything we're doing is just multiplying times 180. Number of triangles times 180. Number of triangles times 180. Number of triangles times 180. So the same thing is going to happen here. We're going to take the number of triangles, n minus 2, and multiply it by 180, which is our formula, right? N minus 2 times 180 for any polygon with n sides. All right, so that leaves us with our formula, n minus 2 times 180. All right, kind of cool. So now let's relook at the sum of the exterior angles of an n-gon. So that was the formula for some of the interior angles of any polygon, but we also proved yesterday, and I'm going to do another variation of the proof today, or at least show you a small difference in the end, about the exterior angles. The exterior angles we saw for a triangle was 360 degrees, but it's actually 360 degrees for any polygon, regardless if it's triangle or quadrilateral. So even as we keep adding more and more interior angles, the exterior angles just shrink, and even though their sum is still going to be 360 degrees, which is pretty cool. All right, so on this n-gon here, we have n sides, we also have n interior angles and n exterior angles. And we notice that the sum of each pair of interior and exterior angles is a linear pair, which adds up to 180. So we have n 180 degrees as well. So the n interior angles plus the n exterior angles, so all of these pairs, all add up to n supplements, linear pairs, which are 180. So we also know the formula for the n exterior angles is n minus 2 times 180. So we can kind of fill in what we know. N minus 2 times 180 plus the n exterior angles, which we don't know what they add up to, even though it's 360 we know, but that's what we're going to prove, is equal to n times 180, which is 180n. The next step here is we want to actually distribute through. Remember, we're going to distribute the 180 through to the negative 2 and to the n. Whenever we do that, we have 180n minus 360. Now this minus 360, that's where the 360 comes in. That kind of balances it out with our exterior angles. And that's why our exterior angles have to be 360, by the way. Plus our in exterior angles is still 180 in. Then we want to get the in exterior angles by themselves. So we're going to add 360 to both sides and subtract 180 in from both sides. If we notice when we subtract 180 in from both sides, that goes to 0 plus the 360, which is just 360, and all of that is equal to the in exterior angles. So regardless of the number of sides, that in stayed constant the entire time. So regardless of the number of sides in any n-gon with n sides, some of the exterior angles is always going to have to be 360 degrees because it's correcting for the -2 that we distribute through, which gave us the -360. So we have the 180 in, 180 in, this -360 and this 360 here have to cancel each other out. By canceling out, I mean they are additive inverses of each other, meaning it adds up to 0 because it all goes to 0. All right, kind of cool. So that was fun. Let me do another version of that. So if you notice, this is very similar. We still have our in interior angles, our in exterior angles for some n-gon, and then we have our in linear pairs, which are the 180 degrees here. Now, what I want to show you differently about this one is that we also, in the proof goes the same. So we still have the same there, there, and there. We distribute that through, which gives us this part, and that part. So it's the exact same proof. And then we're going to add the 360, subtract that from both sides, and we get the in exterior angles has to be 360. So really the same proof. The only thing I want to show you different in this case is that the in exterior angles is really the number of the triangles that we would get. If we go to like some center point or any point in between here, we would have the number of sides triangles, right? So if we have, in this case, 7 sides, we'd have 7 triangles. And the sum of each one of those interior angles is going to be 180, which is the same as one of these linear pairs, which is cool because then we can visualize where that 360 degrees comes from. Oh, so cool. So how many of those do we have altogether? Well, we have in 180 degrees is going to be equal to these in exterior angles. But if we notice there's a missing part, right? It's not just the interior angle. We also have all the angles in the middle, meaning all these interior angles in the middle, the n numbers of them, have to be equal to the sum of the exterior angles. Did you catch that? Because the linear pair is the same as each 180, and all these n interior angles plus the missing angles in the middle, which, by the way, there's 360 degrees of that, right? So that means these blue exterior angles have to add up to the 360 degree angles that are at the center of our polygon, which is fascinating. So you can see we're always going to, regardless of the number of triangles we have there, we're always going to have 360 degrees at the center. What a beautiful proof. So much fun. Geometry, like mind blown. Don't you love it? Aren't you glad you're in honors? All right, really cool. Just absolutely fascinating stuff. And I've never presented that clearly, so that makes me feel good too as a teacher. All right, and that's it. So only 8 minutes, just a quick review. Let's get right into the assignment here. None of this is really new. There's some new applications, but it's all the same basic information. Just make sure we know how to do these. And I will say with this assignment, these problems are modeled after the questions you're going to see on the test. So make sure you know how to do all of them, even the weird ones and stuff like that, because you might see something on the test that looks like it. All right, so on number 1, we have a quadrilateral. It's got 4 sides. So first thing, our name is that it's a quadrilateral. The sum of the interior angles, 4 minus 2, which is 2 triangles, so it's 360 degrees for the interior angles. You can mark it on the diagram if you like. It's kind of nice to do that. So the sum of the interior angles is 360. So that means that all 4 of these have to add up to 360. Well, if we set up our equation right now, the problem is we have 2 variables, x and y. We can't solve for 2 variables at the same time. So the first thing we want to do is solve for x. If you notice, it's going to be the supplement of 130. So we just do 180 minus 130, which leaves us with a supplement of 50. So x is equal to 50. And now I only have 1 variable that I'm solving with the sum of the interior angles of the quadrilateral. So I add all those together and subtract it from 180. Just put it in your calculator, probably on your phone, not a big deal unless you're in class. Wait, none of you guys are in class for this one. This is the one everyone's doing at home, because it's just a review assignment, no big deal. And that should be 100, and it is. All right, cool. And you can cross this out on your answer bank as you go too. All right, number 4, a similar idea. We have 1, 2, 3, 4, 5, 6 angles or 6 sides. So this is called hexagon, or hex angle. And then sum of the interior angles is going to be 6 minus 2 is 4. 4 times 180 is 720. Okay, so some of the interiors are going to be 720. Well, that's all the green angles here. So if I add all the green angles together, I'm going to combine my like terms. So how many x's do I have? That's 5, and 3 more is 8x, plus all the constants. So I'm going to add all the constants together. When I do, I get that number. Oh, it just happened to be 360. That's just a coincidence in this case. And all that's going to add up to the 720, right? So the x terms plus the constant terms adds up to the total of 720. Next step, I want to solve for the x, so I subtract 360 from both sides. That's offset, and that looks more aesthetically pleasing because it matters. All right, then we end up with 8x is equal to 360, and then we divide this by 8, of course, to get x is equal to 45 degrees. So one of the x's is 45 degrees. The next question, really what we need to know is what 3x is equal to. Well, 3 times 45 is 45, 45 is 90, and then 135? Yeah. So that's going to be this missing angle is 135. You could do the same thing, plugging those in, and of course they'll all add up to 720 because that's how we set up our equation, as long as we did the algebra right. All right, so what's the y? The y is an exterior angle, that's why it's blue instead of green. And so we subtract, and the missing part's going to be 45 degrees, I believe. Yes. All right, got it. Good job. Number 5, fill in the following information for the regular polygon. Again, what makes something regular? It's the pretty ones, the ones with all the symmetry, the ones that have the same number of lines of symmetry and also have rotational symmetry. But what makes something regular is all the sides and all the angles are the same. Meaning, unlike the previous problem, if you notice, all the angles were different, which meant that the shape was different, and the sides were different as well. In this case, because it's a regular polygon, we can solve for what one of the angles are, because they all have to be the same because it's a regular polygon. So all the interior and exterior angles are going to be exactly the same for the whole polygon. So on this one, we need to count the sides. 1, 2, 3, 4, 5, 6, 7. All right, so that's a heptagon or septagon. Either ones work just fine. Hepta is the Greek, septa, like September, is in Latin. We used to base our calendar off of the Roman calendar. All right, which started in March. Sum of the interior angles is going to be 7 minus 2 is 5. 5 times 180. So again, sum of the interior angles formula is n minus 2 times 180. The n minus 2 tells us the number of triangles we have on the interior. Like if I drew lines going across here, 1, 2, 3, 4, there's 4 of them, right? So that should be 5. 1, 2, 3, 4. Oh, then the other one's 5. So that's the number of triangles, which is 7 minus 2, always 2 less, because the first 2 sides don't make a triangle. It takes a third one to make a triangle. So 7 minus 2 is 5. 5 times 180 is going to be 900. So sum of the interior angles is going to be 5 times 180, which is 900. Now that I have that, I can solve for one of the interior angles. Let me go ahead and pull up my calculator. So the sum of the interior angles is going to be, there are 7 of them, right? And so those 7 x's all together are going to add up to 900, just like we had on the assignment from yesterday. So let me see what's going on here. So I'm going to do 900 divided by 7, which will give me what each individual angle is going to be, which is 128.6 whenever we round to decimal. Now, for the exterior angles, we've proven twice now, or just kind of a corollary for a month, that they are always 360 degrees regardless of the polygon. So you can fill that in pretty easily. And there are 7 of those exterior angles going all around. And because it's a regular polygon, they're all the same. So we can solve that by doing 360 divided by 7 to figure out what each individual exterior angle is. And if you notice, those two are just supplements of each other. So another thing we could have done is just 180 minus that previous answer we had here, which will give us the exact same number. So again, multiple ways to solve this problem. Kind of cool. Gives us an exterior angle, which is right there. Okay, cool. Should change that color. All right, number 9. This is one of the weird ones, but we're going to do it together, so you don't have to worry about it. If the measure of an exterior angle of a regular polygon, so again, it's a regular polygon, which is important, that means that all the exterior angles are the same. And one of those exterior angles is 22.5. Then how many sides does a polygon have? Well, if you remember, the sum of the exterior angles for any polygon has to be 360. So we don't know how many of sides we have, like in an n-gon. This one I'm showing only 4, but we know when we add all those exterior angles up together, they have to add up to 360 degrees, right? The whole circle in the middle thing. Brilliant. So the question is, how many 22.5 degree angles does it take to get up to 360? So we're doing 22.5 plus 22.5. And then we take that plus 22.5. We just keep doing it over and over and over and over and over again. And eventually we're going to get up to 360 degrees. And we did. Then the only question we have is, how many times did I have to add those exterior angles of 22.5 before I got up to the full 360 degrees that we would have for our n-gon? So different way to do that. It's got to be an easier way there is, of course. So we know our n exterior angles, because there's n of them in an n-gon, adds up to 360 degrees. Well, if each exterior angle is 22.5 degrees, then to solve for the number of sides, you just have to divide 360 divided by 22.5, which I can do in the calculator. So 360 divided by 22.5, just similar to how we actually solve for what each one of those exterior angles is going to be for an n-gon, like at whatever sides it is. but we're just working backwards this time because we know the angle itself instead of the number of sides. So real simple, which was 16. So apparently it took 16 of these angles, and I didn't draw all that because it would take forever. But 16 angles before we actually get up to the full 360 degrees that we would have to have for the exterior angles. So we solved that by dividing everything by 22.5, which gave us n was equal to 16 sides. All right, on number 11, it says again we have a regular polygon, which is important. That means that all the interior and exterior angles are going to be the same. So we don't know the number of sides, but they do tell us one of the interior angles is 140 degrees. Well, we don't know just from the interior angles how many sides we have to have. The problem with that is with the formula is as we keep adding more and more sides, the interior angles, their sums are going to grow without bounds. And so we actually can't solve it that way. But if we look at part A, that kind of leads us in the right direction. So what would one of the exterior angles be? We know the sum of the exterior angles has to be 360 regardless of the number of sides that we have. So our in exterior angles, which each exterior angle they said was 40 degrees, has to be equal to 360. So how many 40-degree angles does it take to get it up to 360 degrees? So divide by 40. When we do that, we get n is equal to 9, which means this has to be a nonagon. All right, number 17, find the measures of the missing angles of the isosceles triangle. We know this is isosceles because of both of these sides are marked to be congruent. This one is not going to be congruent because it doesn't have the same marking. When these are both the longest side, so that means that they're opposite of the biggest angles. We also learned that the base angles of an isosceles triangle are congruent. We proved that 2 days ago, or 2 lessons ago, because I don't know when you're watching this. But what that means is that if this angle here is 62, the other base angle has to be 62 as well. So y is equal to 62 degrees. And now that I have 2 sides of the triangle, or 2 of the angles, I can solve for the missing one because I don't have 2 variables at the same time. So 62 plus 62 is going to be 124. And then if I subtract that from 180, that's going to give me my missing angle of 56 degrees. So x in this case is going to be equal to 56. All right, on number 22, this one is going to be very similar to a problem you're going to see on the test, so make sure you know how to do it. It can be a little challenging because we're dealing with 2 triangles at the same time. So first, let's focus in on the triangle on the left because it has 2 sides, so we only have one missing one to solve for, right? Well, when we add these 2 together, that's going to be 110 degrees, which means the exterior angle here has to be 110 as well. Remember, that's our exterior angles theorem. So anyway, the first way you probably easily do this is the triangles have to add up to 180, right? So if that's 110, the supplement is going to be 70. And then once we know this is 70, the supplement of 70 is the 110. So however you want to solve it, don't mean to confuse you. You'll probably just do it the first way where you get x is equal to 70. And then the supplement of 70 is going to be 110. And now on the other triangle we have here, the purple one, we know these 3 have to add up to 180 as well, right? So that added together is 133. Subtract that from 180, which will give you your missing angle, which is 47 degrees. All right, so that's all the ones I'm going to go through today. So I hope you enjoy your weekend, or if you're watching this on a Monday or Tuesday, if you're a B student, you won't have an assignment on Tuesday, so you can just work on any missing work. Be an excellent opportunity if you had any, of course, missing work from the first semester. That can all be turned in and for the next 2 weeks for full credit, of course. So again, remember, every homework assignment you turn in, your overall grade will go up 2%. So if you have 5 missing homework assignments, get those in, and your grade goes up an entire letter grade. That's pretty generous. So let's just make sure we're taking advantage of that opportunity. I will see you guys later. Have a good weekend, or whenever the time is now. So confusing. See you guys.